Good evening, students. We will start back with where we had stopped earlier. We had spoken till what we had was the properties of the D and F block elements. Last we spoke was with respect to the formation of alloys and all. Now we'll go to the next part, alright, and we will talk about what is the next concept. Some of its oxides, it is clear, and talking about its behavior, whether some are acidic, some are basic, and some are amphoteric. Okay, observe this. First is oxides. We all know what's an oxide, a binary compound of oxygen where the oxidation state of oxygen is -2. That's what we call as an oxide. Second part, what are oxoanions? They are basically the anions with oxygen atom. Those are called as the oxoanions. So have a look at it. What is it? It says all react with metal at high temperature. All metals except scandium form their MO oxides, which are ionic because these are mainly metals. So metal oxides are ionic. And it says what I discussed earlier, in the higher oxidation states, we will see that the covalent character will be more and they will be acidic. In the lower oxidation state, they will be more basic. They will have ionic character. So look at this part, what it says. The highest oxidation state, what we have, that coincides with the group number, and where it says maximum it goes till is still Mn2O7, what you rightly see. Mn2O7, that's dimanganese heptoxide, what we have, where Mn has the highest oxidation state of +7. Then, and what it says, as the oxidation number, look at this part carefully, of the metal increases, ionic character decreases, and Mn2O7 is a covalent green oil. So what I was talking, in lower oxidation state of the oxides, these compounds are ionic in nature and they are basic. In higher oxidation states, the compounds are covalent in nature and the nature of the oxides are acidic. Okay, that's one. Now what it says, more to add over here, that's, look at this part. In higher oxides, the acidic character is predominant. Alright, that's one. Now Mn2O7, that's an oxide, that's dimanganese heptoxide, that gives HMnO4, matlab with water it forms its acid, that's called as permanganic acid. And CrO3, that's chromium trioxide, gives H2CrO4, that's what we call as nothing but chromium chromate, that's the name of the compound. And it gives H2Cr2O7, that's what we call as dichromic acid. Then V2O5, we all know the nature is, however, it's amphoteric in nature. People, amphoteric, we all know what's amphoteric character. It shows both acidic and basic property. Doesn't react with water but reacts with both acids and bases to give salt and water. Then it says, though mainly acidic, and it gives VO4 3- anion as well as VO2 plus salts. So we will see basically that in V2O5 it's amphoteric, but in the other parts it forms acidic or basic forms. Like in vanadium, there's a gradual decrease from the basic V2O3 to less basic V2O4, and then to amphoteric, that will be V2O5. That's one. Okay. And Cr2O3 is also amphoteric. So these two important points to gauge from these oxoions, V2O5 and Cr2O3, both are amphoteric in nature. Okay, that's one. Next, people, what we have to talk now is about two compounds. One is potassium dichromate and the other one is potassium permanganate, along with its methods of preparation. Observe this carefully. Okay, now how is it prepared? It's prepared from the ore. Just see on the slide, please. Chromite ore, that's FeCr2O4, that's the chromite ore what we have. Chromite ore is first made to react with sodium carbonate, where it gets over there, the chromite ore gets converted to Na2CrO4, that is sodium chromate. That's a yellow colored solution, sodium chromate. That sodium chromate is acidified with sulfuric acid, that's H+ ions, where sodium chromate gets converted to sodium dichromate. That's what you rightly see, sodium chromate getting converted to sodium dichromate. And that sodium dichromate, when you react with KCl, that's potassium chloride, then sodium dichromate gets converted to potassium dichromate. I repeat the steps once again, listen carefully. Potassium dichromate prepared from the chromite ore, that's an ore of iron, that is FeCr2O4, first reacted with Na2CO3 got converted into a yellow colored solution of sodium chromate. Sodium chromate then reacted with an acidic medium and got converted to sodium dichromate. And the sodium dichromate, on reacting with KCl, that's potassium chloride, get converted to potassium dichromate. That's one part what we have. And then we have over here orange crystals. Now potassium dichromate are the orange crystals. There's an important question to discuss as it goes ahead. I'll discuss when we come to the KMnO4. Okay. Now potassium dichromate, people, K2Cr2O7, chromium is in +6 oxidation state. All right. That is, it loses all its 6 electrons. Now it says the chromates and dichromates are interconvertible depending upon the P of H of the solution. Meaning, if I say acidic medium, chromate is converted to dichromate. And if it is a basic solution, the dichromate can be converted back to chromate. I repeat, listen carefully. Depending on the pH, you can convert the chromate, that is CrO4 2- to dichromate Cr2O7 2-. So in an acidic medium, see the slide please, chromate is converted into dichromate. Whereas in an alkaline medium, the dichromate is converted into chromate. Okay, that's one. Then next, people, an important point we have the structures of both chromate and dichromate ion. Observe carefully. Cr is in +6 oxidation state in both. Matlab chromium was 24, argon 4s1 3d5. So it's losing all 6 electrons. So look at here, in chromate CrO4 2-, chromium forms totally 6 bonds, so +6. Now how many sigma, how many pi, people? 4 sigma and 2 pi. So hybridized state is always with respect to the sigma. So it's one of the 4s, is this clear? As well as the P. So this is sp3 hybridized. The 2 pi bonds are because of the unhybrid orbitals, but definitely they will belong, in this case of chromium, they will belong to the d orbitals. That's one. And second is dichromate, people, where we say in chromate, if you observe the 2 oxygen atoms, all right, the 2 oxygen atoms over there, their octets are not complete. So to complete the octet, they will gain 1 electron from a nearby metal. That's one, that's chromate. Second, we have, people, that's a dichromate, where there are 2 CrO4 units joined together. Well, look at that structure, where the CrO-Cr, the bond angle, that's important, people, that's 126 degrees. And the CrO-Cr, if you see the CrO-Cr, the bond length, that's one side, it's 179 picometers. And in CrO3 on the one side, the bond length is of 163 picometers. That's what we see. All right. Now in this Cr2O7 2-, if you see everywhere, please look at the structure carefully, people. Chromium is again forming 6 bonds, so it's +6 oxidation state, but we count only the sigma, not the pi for its hybridization. So again here, there are 4 sigma bonds, so again it with 3, 1, 2, 3 and another oxygen. So this is one bridging oxygen and the remaining 3 are the 3 which are at the corner, that's the terminal oxygens. So again 4 sigma, so it's sp3. So just see this part, what is it? Both chromate and dichromate ions, both are tetrahedral, that's sp3 hybridized, where there is a CrO-Cr, matlab it's basically a bridge bond where the angle is around 126 degrees. Clear? Okay, that's one. This is about chromates and dichromates. Next now, people, we're going to talk about the properties. Potassium dichromate, chromium is in +6 state. I right now said in the higher oxidation state, these oxides are good. One, they show acidic nature and their bonds are covalent, and they are in the higher oxidation states, they are good oxidizing agents, meaning they will readily undergo reduction. So that's what exactly is the reaction. Observe this carefully. Dichromate reacting with H+. H+ means what, people? In an acidic medium, it gains 6 electrons and gets converted to Cr3+, and the electrode potential value is there. People, gain of electrons, its reduction. E0 is positive, meaning in the SRP series, it is placed above hydrogen. Now very important, dichromate in an acidic gets converted to Cr3+. Can anybody see what I have written in this bracket here, m/6? Anybody recalls what is it? Do you remember? All right, going back what we did in earlier in mole concept, equivalent mass. Equivalent mass, what is equivalent mass? It's a relative mass. So relative mass which is related to different things in different forms. So if I talk about equivalent mass of an oxidizing or a reducing agent, what was the formula? Molar mass divided by number of electrons lost if it is a reducing agent, or number of electrons gained if it is an oxidizing agent. Here it is undergoing reduction, it's an oxidizing agent, so it's a gain of electron. So the formula, molar mass divided by number of electrons lost or number of electrons gained. Being an oxidizing agent, it's undergoing reduction, so it is gain of electron. So how many electrons it's gaining, people? 6 electrons. That's why m by 6. So the equivalent mass of potassium dichromate in an acidic medium will be m by 6. And being an oxidizing agent, definitely it itself will get reduced. It will oxidize other substances. So they have given some examples. It oxidizes iodide to iodine. So everywhere you will see these elements will all lose electron because potassium dichromate will gain electron. Stannous is oxidized to stannic. H2S is clear over there, is oxidized to sulfur. Ferrous is oxidized to ferric. Okay, so that is what is the reaction, and they have coupled two reactions, that is of ferrous and ferric with the dichromate reaction, and we have got this reaction. And this reaction we can balance how we do now, redox reaction, that is the ion electron method or the oxidation number method in an acidic medium, that way. So ferrous getting oxidized to ferric, Fe2 plus to Fe3 plus by the loss of 1 electron, and dichromate gaining 6 electrons and getting reduced to Cr3 plus. Clear? That's one. Next people compound we have potassium permanganate, KMnO4, that's a dark purple colored compound. We'll talk about its method of preparation. How is it prepared? Just see on the slide please. Is by the fusion of MnO2, that's manganese dioxide, the black powder, what is basically in a pencil cell. We have MnO2 with an alkaline metal hydroxide and an oxidizing agent like potassium nitrate. It produces dark green color K2MnO4, that's called potassium manganate, which disproportionates. I hope everybody knows this. Disproportionation, simultaneous oxidation and reduction of the same species. And in neutral or acidic medium it gives permanganate. So please once again the reactions please. MnO2 reacts with KOH, gets converted to K2MnO4, that's potassium manganate, and this potassium manganate gets converted to potassium permanganate. Okay, now, and it says commercially you can also prepare by one more method, that is what it says, MnO2 is followed by electrolytic oxidation of manganate. Manganate means what we just now did over there, that's K2MnO4, that's potassium manganate. So MnO4, when I'm talking about over here, is this clear? The manganate part, manganate is converted to permanganate then. So what it says in the laboratory, manganese 2 salt, matlab the +2 state, is oxidized by peroxo disulfate to permanganate. What is this? Peroxo disulfate, one peroxide bond between two sulfate ions, SO4 2 minus and one peroxide, that is S2O8 2 minus. That's a peroxo disulfate, and it forms a dark colored crystals which are isostructural, it says, with potassium chlorate, potassium perchlorate, KClO4. The salt is not very soluble, matlab it's less soluble, only 6.4 grams per 100 grams. And KMnO4, if you heat it, it gets converted into, it decomposes back to potassium manganate. So we have two reactions to talk. MnO2, this is a small snapshot people. MnO2, manganese dioxide, when fused with an alkali, then that gets converted to manganate ion, that is MnO4 2 minus, and the same manganate on electrolytic oxidation in an alkaline medium gets converted to permanganate. So MnO2 to manganate to permanganate, that is what is the reaction. So that's the laboratory method for the preparation for potassium permanganate. Now people over here, we're going to talk about the two compounds and their structures and something very important, manganate and permanganate. Manganate, that is MnO4, is this clear over there, MnO4 2 minus, and permanganate MnO4 minus. So here it says both are tetrahedral, one is a green colored ion, other one is a purple colored ion. Let's understand this, what it says. The manganate, once again, why tetrahedral people? Because sigma bonds are 4, so 1s and 3p, so that's sp3. Again the pi bonds will be because of the, pi bonds is here because of its d orbitals over there. So those are the ones which will be because of the anhybrid orbitals. So what it says, the manganate and permanganate ions are tetrahedral. The green manganate is paramagnetic with one unpaired electron, but the purple permanganate is diamagnetic. People, very important line from MCQs for JEE as well as NEET. Listen once again, I'm repeating. Green manganate is paramagnetic with one unpaired electron, but purple permanganate is diamagnetic. Now how do we do this, whether it's paramagnetic, diamagnetic? Very easy, people. What is basically we just now did, what is manganate ion? MnO4 2-. So Mn ka state kya aayega? +6. If Mn is +6, put the configuration. Mn is atomic number 25. So it's argon 4s2 3d5. So two of the first people electrons will go with respect to the 4s. So 2 of the 4s goes. Is this clear? Now, and what will happen, people? Out of the 5, the 4 of the D will go. So how much will be left in D? 3d1. 3d1 matlab 1 unpaired electron. So that's paramagnetic behavior. Okay. On the other hand, let's talk about permanganate. MnO4-. Mn ka oxidation state +7. +7 means what's the configuration of Mn? Argon 4s2 3d5. All 7 electrons are lost. So its configuration here will be just argon. So no unpaired electron. That's why it will be diamagnetic. Clear? Now coming to the color part. Manganate over here it says is green in color. Why? Because if there is an unpaired electron, I discussed this in the color concept last lecture. Any compound has a color only if it contains unpaired electrons. So if there are unpaired electrons, they are present in the d orbital. So that's called dd transition. What is dd transition? Last lecture when I was talking about the complexes, I spoke about crystal field splitting. Okay, when light falls on a particular compound or when the ligand is coming to attack, then the orbitals will split into lower and higher energy levels. So when they split into lower and higher, electron from a d orbital of lower energy jumps to a d orbital of high energy. That's called dd transition. That's one. So when it jumps, it absorbs a particular wavelength of the white light. That's the visible region. Now whatever wavelength of the light is absorbed, the remaining wavelengths are reflected back on the compound. That imparts color. So the green color is a complementary color which is reflected back. In other words, it is the unabsorbed wavelength. That explains why manganate is green color. But something very peculiar. Purple color of permanganate, we right now discussed. Permanganate was Mn was +7. No unpaired electron. So if there is no unpaired electron, we have discussed. If all the electrons are paired or if there is no unpaired electron, the compound should be colorless. Then potassium permanganate is a dark purple colored compound. If you see potassium dichromate, what I just discussed some time back, K2Cr2O7, there also Cr is +6. Chromium is 24. Argon 4s1 3d5. So one of the 4s, 5 of the 3d. It loses all the 6. So both KMnO4 and potassium dichromate have no unpaired electrons. They both have argon configuration, but still both are deeply colored. Why? Very important concept. It's due to charge transfer spectra. What's the meaning of this word? Charge transfer spectra. Transfer of an electron from the ligand to the metal. Catch carefully. Transfer of an electron from the ligand to the metal. So when this transfer takes place, it absorbs a wavelength from the visible light and the rest is reflected. Now what is this transfer of electron from the ligand to the metal? In KMnO4, the ligand is oxygen. Is this clear? So the ligand gives this electron, that is we have the lone pair of electrons. So those lone pair of electrons is what's are given out over there, and that's called charge transfer spectra. Okay. Same way in potassium dichromate, K2Cr2O7, oxygen is the ligand which gives its electron to metal over there. Clear? So both KMnO4 and potassium dichromate are deeply colored because of charge transfer spectra. 1. Now people, we have to talk about certain properties. KMnO4 is basically again a good oxidizing agent because it's in the higher oxidation state of +7. Now in this we have different mediums, acidic medium, basic medium and an alkaline medium. Have a look at it. Everywhere again, potassium permanganate will get reduced and it will oxidize other substances. Okay. Now look at this part, what it says. The pi bond earlier, what we spoke of the structure, that's formed because of the d orbitals of manganese. That's one. Now next, it oxidizes, oxalates to carbon dioxide. Oxalates is basically from oxalic acid, H2C2O4. If you remove the 2H, we get oxalate ion, C2O4 2-. So look at that. Oxalate is oxidized to carbon dioxide by the loss of 10 electron. Ferrous is oxidized to ferric and KMnO4 will get reduced. NO2- nitrite is oxidized to NO3- nitrate. Then the next one we have iodide is oxidized to iodine. All right. So here we have the half reactions where potassium permanganate gains electrons to become manganate, and MnO4 minus becomes MnO2, or MnO4 minus again becomes Mn2 plus, because in MnO2 Mn is in +4 state. All right, that's one. Now next people, we will see in acidic medium. Again I have written here M/5. What is M/5 logic? In acidic medium, KMnO4 is reduced to Mn2 plus. So in KMnO4, Mn is in +7 state. Mn2 plus, matlab Mn is in +2 state. +7 becomes +2 by the gain of 5 electrons. So if it gains 5, equivalent mass will be M/5. Molar mass divided by number of electrons lost or gained. In this case gained because it's an oxidizing agent. 1. Again the reactions here people. Iodine is liberated. So what is happening? I'm just highlighting and I'm talking. Just understand how to interpret it. Iodide is oxidized to iodine, and permanganate is reduced to Mn2 plus, manganese 2 plus ions. Second one, ferrous is oxidized to ferric. Permanganate is reduced to Mn2 plus. Oxalate is oxidized to carbon dioxide. MnO4 is reduced to Mn2 plus. Same way, H2S is oxidized to, over there nothing but H plus and sulfide ions, and the sulfides separately will get converted to sulfur that way. Sulfurous acid or sulfides are oxidized to sulfate, nitrites to nitrates. So these are the reactions basically where KMnO4 will react. So in the exam with respect to MCQ, if they ask, we can balance the reaction as we all know the redox methods, all right, with respect to oxidation number or with respect to electron ion method. Then next is people in neutral or in a what we call as an faintly alkaline medium. In both people we have the formula M/3. M/3 matlab what is happening people? Straight away MnO4 minus is getting converted to, straight away it's becoming to the state of Mn in +4 state. So +7 becomes +4. So it gains 3 electrons, and +4, which is the compound? MnO2. So potassium permanganate ions, MnO4 minus, is reduced to, over there straight away MnO2, that's +4, in which Mn is +4. So if I calculate over there the equivalent mass, it will be M/3. So the gist, potassium dichromate in an acidic medium, the equivalent mass is M/6. Only one for potassium dichromate, acidic medium. There is no neutral or basic medium for potassium dichromate. For KMnO4, 3 mediums. Acidic medium, the equivalent mass is M/5. For neutral as well as basic, the equivalent mass is M/3. Okay, that's one. Same way people, again iodide, oxidation of iodide to iodate. Iodate is IO3 minus. So I minus, here it is -1. IO3 minus, iodine becomes +5. So it's increase in oxidation number. Same way thiosulfate, S2O3 2 minus, is oxidized to sulfate. Then yes people, then we have what it says over there. This note is important people, because for practicals you take potassium permanganate, and when you do the titration you add around 1.5 test tubes of dilute H2SO4. all right, here it says HCl should not be added. So from MCQ point important, why? Potassium permanganate is in presence of HCl are unsatisfactory, since HCl oxidizes it to chlorine. So if HCl oxidizes it to chlorine, chlorine itself also is a good oxidizing agent. Potassium permanganate is also there. That's the reason why we don't use HCl, but we use dilute H2SO4. Okay, then that's in the qualitative analysis. Second part we have people over here, that is in analytical chemistry. The uses are there. That's in bleaching of wool, cotton, silk and other textile fabrics and all, and in the decolorization of oils. So these are some of the uses of potassium permanganate. Now next we have people the second part of the chapter. First we spoke, now D block, we spoke about the properties, what are the periodic functions, and we spoke about 2 compounds, the preparation of potassium dichromate, preparation of potassium dichromate and potassium permanganate and their properties. Now about inner transition elements, that's F block. Why do we call that F block? First of all, where are they present? In the periodic table, in the third group, and the 6th period. After La 57, there is a void 58 to 71. That's collectively the lanthanoids. Why do we call them lanthanoids? The name lanthanoids or lanthanides, it's a prototype. Prototype, an earlier form from which other forms are copied. So from lanthanum, is this clear? That's 57, which is a D block, not an F block. These elements, they have similar properties with respect to lanthanum. That's why they are collectively called lanthanides. And same way in the third group, we have over there nothing but, when I'm talking over there, that is the 7th period. So third group 6th period, we have lanthanides. Third group 7th period, we have the actinides. Actinides, when I'm saying atomic number, after actinium, atomic number 89, there's a void, that's 90 to 103. Those elements are collectively what we call as actinides behind the element actinium. For both these lanthanides and actinides, the electron does not enter the d orbital, but it enters its f orbital. So as it enters the f orbital, we say these elements are called f block elements. Most important feature, lanthanides were earlier called rare earths. So sometimes you may come across this word rare earths because their ores earlier were rare, but nowadays their ores are quite abundant. Alright, mainly magnets and all are being used of lanthanide, all the different lanthanides. Main uses, it's because of its high paramagnetic properties what we have. These elements are mainly used in magnets. Now, these elements, all these lanthanides, they occur in their ore, which is called monazite sand. F block elements are called inner transition elements. They are placed inside the transition elements, and their last 3 shells are incompletely filled. Outermost shell, last but 1 penultimate shell, last but 2 anti or pre-penultimate shell. S and P block normal elements, only valence shell is incompletely filled. D block transition elements, last 2 shells incompletely filled, valence and penultimate. F block last 3 shells incompletely filled, valence, penultimate and pre-penultimate shells. Okay, so this is basically the idea. The 2 transition series, first and second. First transition series is lanthanides, second transition series is actinides. So look here, third group 6th and 7th period, third group 6th period 58 to 71, first inner transition series, and 90 to 103, that's in the third group 7th period, that's the second inner transition series. And then rare earths, what I said, and the ore monazite sand, and then the general configuration. Look at this, NS2 N-1 D0 to 1. So in some cases it's D0, otherwise it goes maximum till 1 electron where it violates off bar, and N-2 goes from F1 to 14. So 3 shells incompletely filled, N, N-1, N-2, N valence shell or the outermost shell, N-1 last but 1 or penultimate shell, N-2 last but 2 or pre-penultimate shell. So last 3 shells incompletely filled. Now we want to talk about people electronic configuration 58 to 71. Okay, listen carefully. The nearest inert gas people, that's going to be xenon, what we have. So xenon, this entire configuration what we see, we don't write the whole thing, we just write xenon. So that includes that's still 54. Okay, we have to write 58 to 71. Now here people, if you observe, look at the elements. Based on this is a mnemonic. I'll tell you all the mnemonic, please write it down. It's a nice mnemonic. First the elements, lanthanum, I'm giving the mnemonic with it, lanthanide, cerium, chemistry, praseodymium provides, neodymium no, promethium problems, samarium since, EU europium everyone, GD that's gadolinium goes, terbium 2, dysprosium that's despo, HO holmium that's Harshad of course, ER erbium extra, thulium TM thorough, ytterbium YB yearly, LU lutetium lectures. So the 14 lanthanides, once again to cap, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Now the mnemonic, listen carefully. Lanthanide chemistry provides no problems since everyone goes to Despo Harshad's extra thorough yearly lectures. I repeat the whole mnemonic, listen carefully. I have made it catchy perpetually so that you people will remember. Okay. Lanthanide chemistry provides no problems since everyone goes to Despo Harshad's extra thorough yearly lectures. So this is the mnemonic with respect to the elements to know. Alright. Now come to the configuration. It's mainly, most important, again, we are discussing lanthanum only because it has similar properties. Otherwise, lanthanum as such is not a F block element. Lanthanum is a D block. So only for consideration only because of similar properties we are considering it. Now let's see. Now we have two configuration. One is ideal or expected, what you rightly see. That's as per of Bohr's principle. And second, we have observed. Observed is actually what we see. Okay. Now there are anomalous configurations. The reason you're going deep inside now, look at those orbitals 6s, 5d and 4f. So you're way inside. So as you go deep inside, orbitals come very close to each other. So as they come close, the energy levels or the energy gaps are less, so the electrons can jump from one orbital to another orbital. Now see here, as per the expected, all are, just see the expected, all are 6s2, 5d is all 5d1, and 4f goes regular, 4f0 to 4f14. Okay, but in observed it doesn't go this way. Look at this carefully. For LA though, anyway it's a D block, so look at that last 6s2, 5d1, so last electron is going in 5d, so it's a D block. Now coming to cerium, it's an exceptional configuration. D should have been 1 because configuration says it should be, look here please, 6s2 is there, 5d 0 to 1 and 4f1 to 14. So 5d 0 to 1, but in case of cerium, one electron doesn't go over here, it straight jumps to 4f and it becomes 4f2. That's the exceptional configuration. Why? Because of less energy difference. That's what I've written here. See the slide please. The 4f subshell has lower energy than that of 5d. So if the 4f has lower energy as compared to the 5d, due to which the electron enters the 4f. Okay, that's one. Then people praseodymium regularly, 5d0 remains, so it's f3, f4, f5, f6, f7. Now again after that, one electron goes back to D. Why? Because now if I see europium here, that element is this, what I'm talking. See the slide please. Here it is 4f7. 4f7 matlab it's become half filled. People's stability rule, empty, half filled and completely filled orbitals are more stable. Now based on that part, so that's why one electron again comes back here. That's for the next one. That's for gadolinium. So again the part 4f7. Then again that one electron jumps back to 4f. It becomes 4f9. Then same way 10. Then 11. Then 12. Then 13. Then 14. And again for the last element, lutetium. Again 4f14 was completely filled. So one electron comes back in the 5d and then goes into 4f over there. So if you observe, the D1 is only at 3 place. LA, where it is D1, where 4f was 0, so empty. 5d1 is coming again, where that's in gadolinium, where 4f7 half filled. And again 5d1 is coming, where last part 4f is 14, that is, it is completely filled. So empty, half filled and completely filled orbitals. That's the part when we have the D1 configuration. In the exam, with respect to MCQ or from the HSC part, whenever the question is asked, you're supposed to always write the observed configuration. Only in MCQ specifically it comes, the ideal configuration is, or the expected configuration, that word should come. If I just say configuration is, always write observed. Clear? That is one. So there's 3 shells in completely filled, 6s, 5d and 4f. That's one. Now coming to the second point, 2 more things we're going to discuss: atomic size and its oxidation state. That's it. Now in atomic and ionic size, if you remember, in periodic table, I discussed about lanthanoid contraction. That's what we see here. What exactly is this lanthanoid contraction? Now see this graph carefully, people, everybody. La3 plus, all show more stability in plus 3. And last, if I go to Lu3 plus, lutetium. People, if you see carefully, all right, La3 plus was if I come, or if I start from cerium, let's say, because La3 plus though is the D block element, if I start from C3 plus, okay, roughly if I see somewhere around 59, and this goes till 71, all right. So technically, if I have to say the ionic radii 59 around if I have to say, so that's coming to how much? 11 picometers approximately. Okay, so what is this part? There's a very small decrease. Question is why there is such a small decrease. All right, what is lanthanide contraction? With respect to lanthanides, electron is entering into its pre-penultimate, that is n-2 f sub shell. Now shielding of electrons is S greater than P greater than D greater than F. So F shielding is very poor. So due to poor shielding, F electrons are not contracted, but the valence shell electrons are pulled more towards the nuclei. That is because we have 3, 6s, 5d, 4f. So if 4f pull is not more towards the nuclei because it's in the f orbital, 6s ka pull is more. So that gets pulled more. So if the 6s gets pulled more over there, the size will contract over there. But because of the poor shielding, the decrease in size is very, very gradual, or it's a very small decrease. And it is because of this small decrease, which is called lanthanoid contraction. The elements post lanthanides, I discussed this last time, we have chemical twins, 4 pairs of chemical twins, meaning elements where up and down the group, technically up and down size should increase, but their size remains almost the same. All right, that's called chemical twins. The 4 pairs: zirconium, hafnium, molybdenum, tungsten, technetium, rhenium, and niobium and tantalum. The 4 pairs of chemical twins which have similar size due to a very small gradual decrease in the atomic and its ionic radii. That's called lanthanoid contraction. So the decrease is very, very small due to the poor shielding of the F electrons. That's what is the whole part explained here. And this is the last part on moving from C to Lu. Decrease in ionic radii is 18 and atomic radii is by 10 picometers. So the decrease is very, very small over there. Okay, that's one. Now people comes the last part what we have, that's oxidation states. Observe this carefully. From cerium to lutetium, everybody shows +3 state. Matlab +2 is also there, but mainly stability is maximum in +2 oxidation state with respect to lanthanides because of electrons from 3 shell, one of the 6s, one of the 5d, and one of the 4f. Now what is the observation here? Very simple. Lower oxidation state, the elements are good reducing agents. So +2 reverts to +3. And in higher oxidation states of +4, they are good oxidizing agents. So higher one is +4, that reverts back to +3 that way. Some cases we also have +5, that is basically in some of its complexes it shows. Otherwise mainly the +1 and +5 are mainly with respect to the complexes. Otherwise mainly it's 2, 3, 2, 3 and 4. That's how it goes. All right. So see this part what it says. We call these lanthanide compound as Ln3 compounds. Ln is the basically what we call as a prototype. Ln, that's a short form for all lanthanide elements. They are prominent. They occasionally show, these are the 2 states mainly, +2 and +4. So in +2 reducing agent, +4 oxidizing agents. Now what it says, cerium 4+ achieves a noble gas configuration because it's a good oxidant. It's a good oxidizing agent. So that's why I look at that value. Its E0 value is plus. Matlab in the SRP series it is placed above hydrogen. Secondly over there it's a good reducing agent. Acha. Then PR, praseodymium, neodymium, terbium and dysprosium, they exhibit +4 state only in their oxides. So if they are +4, these are good oxidizing agents. Europium 2+ is formed by losing 2 electrons and it has F configuration, F7. Now europium 2+, if it has F7, matlab it is more stable. Now europium 2+, matlab the state is +2. So +2 will revert to +3. Matlab it's a good reducing agent. So +2 will increase to +3. So EU2+, europium, that's a strong reducing agent. And same way YB2+ will have F14, ytterbium. If you lose 2 electrons, is this clear? Then in the configuration we have is +14. So in 5b2 plus in plus 2 state, it's going to be a good reducing agent again, where plus 2 will revert back to plus 3 over there. Okay, so these are the common states. Common state of all lanthanides plus 3, lower end plus 2, higher end plus 4. Okay, then yes, that's it people. We are done with this part. All right, next class I'll continue with the properties of the F block elements. Thank you.